Okay, I want to do a quick sheet here now on just revising the ellipse, the parabola and the hyperbola by the eccentricity method, and what I think is a good practice exercise there now, because this is not teaching the concept, this is a revision activity really, but I want to just link it back to the solid cone, because basically an ellipse, a parabola and a hyperbola are all shapes that can be got by cutting a cone. Now I know an ellipse can come from cutting a cylinder as well, but mathematically a cylinder is a cone with just a very gradual slope in it. So I'm going to start with looking at the ellipse. Now if you cut an ellipse with an inclined plane like this, okay, so there's our inclined plane. That will give us a cut section on the ellipse, something like, or on the cone, that's going to look something like that. Okay, so that's our cut section, which is in the shape of an ellipse. And here's the rest of the cone there. I'll just heavy that in now. So I can put it sitting on a surface if I want. Okay, so there's our ellipse. Now, mathematically, the eccentricity is the distance from any point on the curve to the focal point over the point to the directrix. Okay, and again, this is something now that you would have covered before, and in an ellipse the eccentricity is always less than 1. So in this example I'm going to say it's going to be I'd say maybe 4/5, or if it was given as a decimal it would be 0.8. Alright, so starting off with that, I'm going to just draw a light line here for an axis all the way across. Now we're going to draw all three of them one after the other. You will note there I give a slightly bigger distance to the ellipse, slightly, rather than the other two, because the ellipse tends to go a bit wider. So what you want to do there now is you want the left hand side there, we'll just put on a random directrix, and I'll build all three of them up at the same time. There's the directrix for the parabola, and this is going to be the directrix for the hyperbola. Okay, and with the ellipse now, I said that the eccentricity is 4/5. So if I come out 5, and I go up 4, 40, so I came out 50. And I went up 40, so that is the eccentricity. So I'll just eccentricity is 4/5. Now it's always less than 45 degrees for an ellipse, and for a parabola it's always exactly 45. For a hyperbola it's always greater than 45. Okay, so let's deal with this one now. And my next move here now is I'm going to pick and keep this in closer now. This is going to be one of the focal points for the ellipse. Now you would be given that, so I will, and again, just to keep them all the same, I'm going to just put the focal point or the focus in for all of them as well. Now, and I will build up all three of them, I think, in the one go. So always for the parabola, the eccentricity is 45 degrees. And for the hyperbola here, if it's given mathematically, you could be told it would be maybe 1.2, which would be, if I came in 5 and I go up 6, so we can see there that's clearly greater than 45 degrees. So 45 degrees here is equal to 1, which means if you came over 40 and up 40, or over 50 and up 50. So that's them all set out. You put a directrix, pick a focus, put on an eccentricity line like that. So in all three of them there now, if you go a 45 degree angle and straight down from the focus 45 and down, that is the vertex. Now only for the ellipse you can go 45 degrees in the other direction and down, and that's the other vertex. Now for the parabola, 45 degrees and down is the vertex, whereas obviously if you go 45 degrees in the other direction, it will never hit for the parabola. And the same with the hyperbola, 45 degrees and down gives us the vertex, and same as the parabola, if you go 45 degrees in this direction, it will never meet. So you've only got one vertex in a parabola and a hyperbola, 2 in the ellipse. Now the next move then is always vertical from the focal point there, or the focus, is a very, very important line called the Lattice Rectum, which is where the Lattice Rectum intersects or hits the line of eccentricity, is always a point on the curve. So that's a point on the curve, that is a point on the parabola, that is a point on the hyperbola. So once you know that, and because it is symmetrical, you can take that distance and step it down. So we now have a couple of points on all of them. Now to finish it off there, then what you need to do is take some random lines called ordinates, and we're going to find 2 points on every ordinate, one up here, one down there. Okay. Okay, so there's all our ordinates taken, as I said, randomly. Now, going back to our eccentricity, which I spoke about earlier on, from a point to the focal point, point to the directrix, that is the mathematics of that line, and every point on the curve obeys the maths. So my method for doing it anyway, I know this isn't the only way, is that is the distance of the point on that ordinate from the focus. Move on to the next one. Take that vertical height up to the line of eccentricity. That is the distance of the points on that ordinate from the focus, and so on. And it's the same for all of these curves. And I guess that's what I was trying to convey by doing all three of them together. So you can see there that the curve is starting to come back down because it's an ellipse. Now, if you wanted, and it's probably a good idea if you're doing an ellipse, you could get the middle. You could get the middle. Okay, as it turned out, this is pretty much the middle. So I just got lucky here. But you could take an ordinate exactly in the middle to find the minor axis. But that actually, it's within a millimeter of it, so that's close enough. So there's all our points. So I'm going to draw my ellipse first. Now remember, it's a tangent, so the curve always goes through the tangent, or through the point where the lattice rectum there intersects the line of eccentricity. So that's half our ellipse. Okay, so there's our ellipse, and I'm just going to make a note there of, I might just put a color on this because it might help people. This particular ordinate that one is called the lattice. Okay, and where that intersects with the eccentricity is always a point on the curve and same distance below as well. So same thing there now, moving on quickly there now, because it's the same procedure with all of them there then. So that is the distance, the PF on that ordinate. Vertical height there, that is the distance for the point on that ordinate from the focus. And the same here. So that's all the points that we need, and again we can draw our curve. Okay, so there's our parabolic curve or parabola, and I am going to color in again the lattice rectum. I'll just write down LR here for that one because it's already written down over there. And finally, there's our distance point to the focal. Point to the focal. And finally, okay, just need to extend these ordinates down a tiny bit. So here's all our points. I'll just dot them in there a tiny bit. just a minor detail here, but you can, the same rule applies. If you want to find a point at the other side on the left between the focus and the vertex, the same rule applies. It doesn't make a difference. That is the distance from the focus to the point on that ordinate. Okay, so here's our hyperbola. And then the sun comes out. Okay, so all that remains there now is, I just want to explain there that, like I did in the first one here, that the parabola comes from cutting a cone parallel to the side of the cone. Okay, cutting a cone parallel to the side of the cone, and in 3D there it would give you then a cut section kind of like this. So that would be our parabola in a 3D situation. I'll just heavy in the remaining part of the cone here. And I'll put that sitting on a surface. And a hyperbola then comes from cutting a cone parallel to the axis. So if you chop that off there parallel to the axis, it's going to give you in 3D a shape like this. Just put that on the surface as well. Okay. And again there, just gonna color these in. I just put a tiny bit of color on these again. I always think it helps the understanding. So this is the horizontal plane. Horizontal plane. You'll notice I'm covering the horizontal plane in here now, because in theory that part of the cone is chopped away. And I'll just put a color on the cone there then as well. Okay, so true shape of the ellipse, true shape of the parabola here, and hyperbola there, and that is drawing them using the eccentricity. And just to finish it off there, just going to write that down there. So the parabola, the eccentricity is equal to 1, i.e. if you came over 20, it'll be up 20. And for the hyperbola, the eccentricity is always greater than 1. So it might be something like 3 over 2 or 5 over 4, something like that. Okay, so that is a very good revision sheet for just drawing all of those 3 sections using the eccentricity.